So this time, a proton is placed in an electric field between two parallel plates. Okay, similar kind of scenario here. If the plates are 6 meters apart and have a potential difference between them of 75 volts, how much work is done against the electric field when the proton is moved 3 centimeters parallel to the electric field?
What is 6 parallel places? That even have to use the is there like certain?
Yeah, so
That's what limits it to?
that's right. When you have a uniform field, you can't use KQ over R squared. That's the rule, because that KQ over R squared is saying like, okay, charge increases when you get closer or decreases when it goes far away. So yes, then you are limited to the rest of them, where you're, yeah, because it's saying, okay, it's the same way. Okay, so here, we are going to have to use our idea of work, which, as Kim showed us earlier, work refers to change in energy, right? So that will help us out too. Okay. Okay, so let's get started. So, our proton, stuff we know about our proton, let's write this down first. We know our charge of our proton is 1.6 times 10 to the negative 19 coulombs. Our mass of our proton we know is 1.67 times 10 to the negative 27 kilograms. We are told our delta V is 75 volts. Our D between the plates, so I'm going to go D plates, is equal to 6 centimeters. Divide by 100 and I get 0.06 meters. Now, the distance that the particle moves, or that the proton moves, is 3 centimeters. So that's 0.03 meters. So what we want to end up finding is W, okay? Work done, or the change in energy. Work done is, we can say it's like F times D. Okay? So, because we're not given speed here, so we can't find delta E using speed. So we're going to have to use delta E, or work, with the force exerted on the amount of distance. Okay, so because if we think about it, the electric field is exerting a force, right? It's always exerting a force. So a force is being done on that proton to move it a certain distance, right? That's what work is. Work is the force exerted on an object over a certain amount of distance. See that? How it kind of plays in to the particle world? Okay, just want to make sure that we're together on that. Okay, so this is then the distance that the particle has moved, okay? And I can say specifically my force is electric force, okay? And I'm going to put my arrow over top because it's directional. Well, I was given distance here, but I wasn't given FE. So what I'm going to have to do is I'm going to have to find FE. Now, as Lisa mentioned, we can't use Fe equals KQ, or the KQ1, Q2, etc. So we're going to have to use the other formula, where we have E is equal to Fe over Q. But, it's going to be multiple steps here, but we're not given our electric field strength, okay? But we can find it because we're given the voltage of the actual plates and the distance apart they are. So we can find this one. Oh, it's black. We can find this one using E is equal to delta V over D of the plates. Okay, so the order we're gonna do this, we're gonna do this question, or this formula first. Then we will do this one second, and then this one third to get our final answer. So there'll be 3 steps to this one. And this is kind of how I want you guys to organize your information, is start with what variable am I trying to find out? And kind of work your way down, because you're going to have to do multiple steps for a lot of your questions. So we have 75 volts per 0.06 meters. So my electrical field strength is 1,250 volts per meter. Now remember, since I'm not moving the plates or changing the battery, okay, my electrical field strength stays the same. So I can now apply it to my second formula, okay? So I want to find out how much force is being exerted on this particle. So I'm going to rearrange to solve for Fe. So Fe equals 1,250 volts per meter multiplied by the charge of the proton, which is 1.6 times 10 to the negative 19 coulombs. So my Fe is equal to 2.0 times 10 to the negative 16 newtons. Okay, now then you can do your third equation to find out work now that you know the force that was exerted on the particle that moved. So W is equal to F E times by the D of the particle. So this was 2.0 times 10 to the negative 16 newtons multiplied by 0.03 meters. So this is 6.0 times 10 to the negative 18 joules. Now, you may have been asked to find out the work done measured in EV. So how would we convert this into EV? What would we do? For every 1 EV is 1.6 times 10 to the negative 19 joules. Okay. And if you don't remember that, look here on your data sheet.
What does it say for the?
It's not, I'm just saying if in the case you were told to answer it in EV, I just want to practice that with you. So if you forget, it's right here in constant under electron volt. Okay?
Did you multiply it by that?
Okay, so if I set up my fraction now, I'd say I need to find X amount of EV, needs to be both on the top, if I'm doing a fraction like this, and then 6.0 times 10 to the negative 18 joules. You cross multiply and solve for X. So 6.0 times 10 to the negative 18 joules multiplied by 1 EV is equal to 1.6 times 10 to the negative 19 joules multiplied by X EV. how do I solve for this? I divide 1.6 times 10 to the negative 19 joules. My joules cross off and I'm left with EV. So 38 electron volts. So both are right answers. I just wanted to make sure, that we practice this, because if you're met with that it says to put it in EV and you're like, what the heck is that? I want you to remember that EV is like the same as saying energy or joules. Okay? So get familiar with that.